Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and today we'll try to discuss the orthogonal trajectories in the light of Cartesian coordinates, in other words what you say rectangular coordinates. So what exactly the orthogonal trajectories are? Like, for example, I just say that I'm discussing a curve. For instance, it looks something like this. It's having some kind of equation. We just call this equation as f of x, y, c. Okay, so I just pick up one point on this curve, and on this point I just try to draw a tangent line. Okay, this is tangent line, quite rough, but it is. That's it. Now, with respect to the same point of tangency, I just try to draw another curve having some different equation, and it is going to intersect this point of tangency like this. Okay, and it's having some different equation. I just call this equation, I just represent this function as f of x, y, k. Okay, it's just an arbitrary representation just to get an idea. Now, at the same point of tangency, which is also the point of intersection of these two curves, I just draw the tangent line with respect to this second curve. It looks something like this. Okay, so this is your T1, this is your T2. You can take it in that sense. So if these two tangents, which are representing the tangent of this curve and the tangent of this curve, at this point of tangency, if they are perpendicular to each other or orthogonal to each other or normal to each other, forming a 90 degree, if this condition is getting satisfied, then you will say that these two curves are orthogonal trajectories of one another. Okay, simple as that. So if I say that I provide you an equation of first family of curve, presently I have just drawn here single curve. If there are multiple of curves representing the same function with respect to different values of constants, you're going to have a family of curves here. So if I just provide you a general equation of the family of curve of Z1, and I ask you to find out the equation of the orthogonal trajectory of the second family of curve, what is the method? That's the topic of today's lecture. Okay, so I just say that we have studied in the derivatives what exactly derivatives are. It's the instantaneous rate of change or the limit of the slope of the tangent, right? So if I talk about the instantaneous rate of change or the limit of the slope of this tangent 1, when I try to differentiate this function, I'm going to get the value of the slope of this tangent 1, right? I just represent this tangent with some value like this. Okay, it's definitely going to appear in the form of function. So this is it. So this is the slope of this tangent of this first family of curve, right? This is it. So as this tangent is orthogonal or perpendicular to tangent 1, right? So it means that the slope of this tangent can be expressed as the negative reciprocal of this slope, right? So when I get this thing, then I can get I'm going to have definitely a nice differential equation that I can solve either by several methods we have discussed in the previous videos. It could be through separable method, it could be through exact value method, it could be through linear method, it could be through homogeneous, it could be through Bernoulli. So it depends on the nature of the equation you're going to get after following this tactic. Okay, so I hope a little bit concept might have been cleared in your mind. Now we move to our examples. Okay, so once the examples will be gone over through, then definitely the concept will get further strengthened in our minds. All right, so let's go over through the examples. Okay, so this is our first example. Now over here we are provided a general equation or a standard equation of our circle having where the radius value is not exactly specified. Okay, so you are going to have a family of curve once when you just substitute different values for c. Okay, so if I just put c value half, then you're going to have a curve having radius 1 upon 2. Okay, so it looks something like that. Let me just draw it in a rough sense. Okay, this is your half, 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 half. So this is going to be a circle. Having half, 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 and half, right? That's it. So this is for your x squared plus y squared equals to something like this. Now, if you just put x squared plus y squared and the place of c you just put 1, is 1 square. So it is going to be second curve. That's how you just obtain the second curve. So I'm just trying to draw in quite rough sense. It exactly doesn't look like a circle, but I hope you just cooperate with it. So that's it. So you see, for the different value of c, you're going to have different circles. A family of circles are going to be obtained something like this. Okay, so now we have to obtain the equation of second family of curve, which is going to behave orthogonal on these set of curves, okay, at different points. So what is the way? First of all, we just differentiate. I just call this equation as equation number 1. All right, so we just make a solution heading nicely, and now we just differentiate this equation with respect to our x. So with respect to x, so once when we just differentiate entirely, so you see this is a constant, so derivatives definitely going to be 0. So this is your 2x plus 2y dy by dx. All right, so on simplifying, we just come to know that dy by dx is equals to minus 2x upon 2y, which is minus x upon y. Okay, so this is the equation of the slope of the tangent at any point that you are going to draw. Okay, you just select this point of tangency, you just draw a tangent. The equation of tangent is going to follow this equation. Okay, this for this value of x and this value of y and so forth. If you select this point of tangency, you just draw a nice tangent. For this value of x and this value of y, you're going to have the value of the slope of the tangent with respect to this equation. Okay, that's how this equation is going to help you. Now we have to find out that tangent that should be perpendicular to this tangent. It should be perpendicular to this tangent. Okay, so we have to find out the slope of this tangent, right, this one. So what we do, we come to know that as these two lines are perpendicular to each other, so the slope of this line is going to be the negative reciprocal of this slope, right? So the slope of tangent of the orthogonal trajectory curve, or you just directly say the slope of the orthogonal trajectory, it means the same thing. Okay. Trajectories of set of equation number 1 is going to be dy by dx equals to negative reciprocal of this slope, which is going to be y by x. Okay, that's it. So now what we do, we are going to swap the values here and there and try to get a nice differential equation, then we'll try to solve it out. Okay, in order to get the equation representing orthogonal trajectory family of curve. Okay, so once when I just swap the values here and there, that's a differential equation I'm having, and it is following the first type of linear first order differential equation that we solved through method of separating variables. So now we have just separated the variables. Now we are going to integrate both sides with respect to the corresponding variables that we are just trying to deal with. So it is going to give me log of n log of y equals to log of x plus some constant here plus some constant here. So I'm just writing constant just on one side, okay? And that constant could be c, okay? I can represent this c constant by log of some other constant number, okay? Just to make a nice format, I can write this constant value as the log of some another constant number, right? So now by following the condition of the logarithms, now once when I take anti-log at both sides, then this ln is going to be cancelled, so I can cancel it directly too, okay? So I just canceled it directly. So y is equals to kx. So now you can see this is equation of a linear line, or equation of a straight line passing from the origin, because you can see the y-intercept is 0 here because it is following this format, equation of linear lines or straight lines. So you can see this, the y-intercept is 0 here. So all the lines which are passing from the origin, you can see all the lines which are passing from the origin, okay, so they are right perpendicular to the tangent of the circle family of curves at a certain point of tangencies, okay? So these lines are the family of orthogonal trajectories to this family of curve, okay? So that's how you obtain the equation of the orthogonal trajectories. That's it. Now let's move on to the one more example. I hope the concept is getting clear in your mind. Now this is the equation of another family of curve, all right? And we have to find out the equation of those curves which are orthogonal to this family of curve, okay? This is the value of c. For different values of c, you're going to have different curves representing the same equation, okay? So now what we do, we just differentiate both sides as usual with respect to our x. I'm not writing the statements just to save my time. Okay, so we just take a nice derivative here. Exponential, and then we just apply a nice chain rule on the power value, and I just use a big bracket here instead of small. So this thing is giving me negative c by 4 e raised to the power negative x by 4. Okay, so this is the slope of the tangent lines that we are going to draw on this family of curve at different point of tangencies. All right, so that's it. So as far as the slope of the tangent of the orthogonal trajectory curves are concerned, they are going to be the negative reciprocal of this slope. So it is going to be negative reciprocal of this slope. Okay, so it is going to be 4 upon c e to the power this. Okay, that's it. Now what we do, we are going to perform we are going to manage a nice differential equation by swapping the values here and there. Let's see what we get here. So dy equals to, I just move this differential over here, so it becomes something like this, and we are having negative power here, so it moves upwards, becomes positive. So dy is equals to 4 upon c e power positive x by 4 dx. Now we integrate both sides with respect to subjective variables. This is a constant thing, so it is going to be written definitely outside the integral. So it is okay, so we are having y now the exponential integral is the exponential itself upon the derivative of whatever the power you're having on the exponential plus some constant. Okay, this 4 will go above, it becomes 16c c x power 4 x upon 4 power n x plus some constant. Okay, how about if I just try to make a nice format? I just move this exponential over here. And I just make a nice adjustment. Plus some constant. So you see this thing is equal to y. So how about if I just replace this thing with y? I can leave it as it is as well, but I'm just trying to beautify the format, nothing else. So it is plus some k. Okay, so this y will move here, it becomes y square equals to 16 upon x plus some k. Well, I think I've done a little mistake here, which is indeed giving me a big difference in the answer. The mistake that I did over here is the derivative of this thing. The derivative of this thing is going to give me 1 upon 4, right? It's going to give me 1 upon 4. It is going to give me 1 upon 4 plus some constant. And this 4 goes over here, it becomes 16c, and just 1 is going to be left in the denominator. It means nothing. That's something that we do not represent. Okay, so I'm not having anything here. So just 16 is left, and this is going to be your 1 upon y, and this 1 upon y will go right over here. So before that, we should take some, I better cancel out this thing. So before that, we should take it is 16 upon y plus some constant. Okay, but this is said to be the equation that you can either further solve or you can stop over here as well. So if I just write it like this, and we take nice LCM, it's y squared minus 16 upon y equals to k. Y squared minus ky equals to 16. So this is going to be the equation of the orthogonal trajectories, or the equation of the family of curve which is going to be perpendicular, or whose tangents are going to be perpendicular on the tangent of these set of curves, this set of curves at different point of tangencies. So that's the way how we just try to evaluate or try to explore the orthogonal trajectories of a certain set of curves. So this is something that we have just tried to understand with respect to the Cartesian coordinates. Inshallah, in the next video, we'll try to approach to solve the orthogonal trajectories with respect to the polar coordinates. So if you find this video helpful, subscribe my channel, hit on the like, and share this video with your friends and other learners. Take good care of yourself. Allah Hafiz.